Hello everyone, welcome to the lecture 46 in the course Diffusion in Solids. So, we have started or rather we will now start talking about the diffusion in various classes of materials. So, we will take up several classes of materials like intermetallics, semiconductors, ionic solids, metallic alloys, nanocrystalline alloys, quasi-crystalline alloys and so on, and see some of the diffusion aspects, some important diffusion features in these alloys. So, the general principles that we have covered so far, be it the Fick's laws or the mechanisms or in the case we also saw interdiffusion or the random walk theory. So, the general principles remain more or less similar, but then there are certain key features which differ from each class of material, and that is why it is important to look at them. So, how for example, there will be diffusion, activation, enthalpy in everything, but then that diffusion, activation, enthalpy may have certain correlations and so on. So, we will look at some of these aspects. So, today we are starting with diffusion in intermetallics. So, intermetallics, as I think many of you might know from the physical metallurgy, that they are the compounds where you have two metals or a metal and a non-metal, and usually they are characterized by an ordered structure. So, these usually form at you can have line compounds which form at a fixed composition, or you may have certain intermetallics with wider phase field. If you recollect, we took some examples when you were talking about the phase growth in interdiffusion. Some compounds have a narrow phase field or they are line compounds, some have a wider phase field, and these are usually found in the center of the phase diagrams. Now, because of this ordered structure, the diffusion mechanisms in intermetallics become more complicated. So, we will see very soon why it is so. Although the defects that are involved like vacancy are still involved, but in a slightly different way. So, there are several classes of intermetallics that are present, and depending on the structure. For example, here is L12 ordered phase, the classic Ni3Al, Ni3Ga, Ni3Ge combine to form such an intermetallic. Here these are ordered structure. So, if you see in an X-ray diffraction pattern, it will generate superlattice reflections, because now if you consider BCC, in BCC although, or FCC for example, since we are talking about L12, in FCC if you talk about a solid solution, then any atom can occupy a corner position, another atom can occupy a face centered and vice versa. Whereas, when you talk about ordered intermetallic, so for example, here A occupies the face center and B occupies the corner, and you can see that the corner atoms of B, there are 8 corner atoms. So, effectively one B atom, and face centered you have 6. So, each face is shared by 2 unit cells. So, you have 3 A atoms. That's why it is a stoichiometry A3B. So, this is a L12 ordered structure where A atom occupies only FCC, only the face centered, whereas the B atoms occupy the corner. Similarly, you have other examples. For example, B2 is a very important class of intermetallics, NiAl, CoAl, copper zinc, gold zinc. These all crystallize in the AB B2 ordered structure. So, here the B atom occupies the center and the A atom occupies the corner. So, you can again say the effective number of atoms, one of each. You have a more complicated structure where you have A15 ordered phase. You have L10 type of structure, Cu, Au, cobalt, platinum, iron, platinum, and so on. So, there are several types of intermetallics. This is not a this is not a completely exhaustive list. Here I have tried to give more type of structure. So, for example, this is, you can see already this looks more complicated. This is DO3 structure which is shown by Fe3Si, Cu3Sn, Cu3Sp, Ni3Sp and so on. You have DO19, C15 which are Lewis phases. So, intermetallics usually if you see from a mechanical properties point of view, their content, if it becomes too much, then it makes the material brittle, and then that perspective they are not desirable. However, intermetallics, if you can put in a controlled fraction like you do in superalloys and so on, then it can give you a very good strengthening of the alloy. So, and in addition, intermetallics also find a lot of use in functional applications, and they are hard. So, they can be used for a variety of applications where such strength is required. Now, many of the intermetallics undergo an order disorder transition. So, they have an ordered structure at lower temperatures, but as you heat up, then beyond a certain point they start becoming disordered. Not all the intermetallics show this kind of transition. Some intermetallics remain ordered up to their melting point, but there are certain cases. One classic example is copper zinc, which undergoes a order disorder transition. Now, when that happens, so for example, if you see zinc and copper, zinc occupies the body center, copper occupies the corner. So, when it undergoes order disorder transition around 741 Kelvin and becomes a disordered. So, here when we write 50%, that means there is a 50% chance for copper and zinc to occupy body center as well as corner atom. So, that means there is no preference once it becomes disordered. So, this kind of a transition leads to the change in the activation enthalpy. Here this delta H represents the activation enthalpy of self diffusion of copper and zinc in these two structures, and the delta H in the structure which is an ordered structure, B2 structure, is more than the delta H in a disordered structure. Similar thing has been observed also for cobalt iron alloy, for iron self diffusion in Fe3Al. So, basically you have the ordered structure when it becomes disordered. So, the activation enthalpy decreases, and you will have a higher diffusion coefficients. And you will be able to appreciate this more when we talk about now the mechanisms, because you will understand that why activation enthalpies are higher in the case of ordered structure. So, there is an activity question for you that order disorder transition is a first order transition. Is it true or false? So, when we talk about phase transformations, we talk about first order transition, second order transition, which are defined with respect to the changes in free energy. So, you just find out for your own knowledge whether it is a first order transition, is it true or false. Now, let us talk about some features of diffusion in B2 intermetallics. So, what in this B2 intermetallics, in fact, this is also true for other intermetallics as well, what is known as the coupling of diffusivities. So, in most of the binary intermetallics, the diffusivities of constituents are nearly same, okay, less than one order of magnitude difference. So, for example, in copper zinc, d zinc by d copper is about 2.3, whereas in cobalt and iron it is almost equal to 1. So, this what it indicates is that the diffusion of both atomic species is mediated by the same type of defects. That means, they are somehow participating together in the motion of atoms. So, therefore, the vacancy type defects move in a highly correlated way to preserve the equilibrium degree of long range order. So, this is the reason. This is the main reason, because it is an ordered structure. So, any jump sequence or any exchange that happens, ultimately that exchange should ensure that the order is preserved at that particular temperature, if the equilibrium structure is the ordered structure. So, in that way that a simple exchange may not ensure that. So, that is why you will see very shortly that multiple jumps are required to ensure that the exchange of atom and the vacancy or exchange of the atom and the defect happens such a way to preserve the long range order. And because of maintaining the long range order, it is often required that both the atoms participate in this jump sequences, and hence you see the diffusivities being very similar to each other of the constituents. So, for example, for intermetallics, especially the ionic solid, sublattice diffusion of each component via second nearest neighbor jumps is also possible. So far, we always talk about the diffusion happens to the exchange happens with the nearest neighbor. But some cases we will see more in the ionic solids when we talk about that second nearest neighbor jumps are also possible. So, in as far as the B2 intermetallics is concerned, since the diffusivities are similar, so sublattice diffusion is not the possible mechanism here. So, what are the mechanisms when it comes to the B2 intermetallics? So, as I already indicated that these mechanisms are more complicated because the long range order has to be preserved. So, we will show some examples now. So, the first mechanism is called as a 6 jump cycle mechanism. So, as the name indicate, there has to be 6 jump involved for one exchange to occur, such that the order is also preserved. So, it depends upon the direction of the displacement, how the jump sequences will be. So, we will take an example of a case where the net displacement occurs in the 110 direction. So, let us say you have this kind of an intermetallic structure where this green atom represents A, the open circles these represents B, and this cube represents the vacancy, the gray color. So, if you see this first structure, you have this is the A sublattice, this is the B sublattice, and you have a vacancy on the A sublattice. So, here this is indicated as a VA. Now, this first jump sequence, let us say the first jump, that as it is indicated by the number 1. So, vacancy exchanges its position with this B atom here. So, what will happen? How will it look like now? So, what happens is the B atom has now come here and the A atom has come here. So, the vacancy has come here. So, now what happens is that you have a vacancy at the B side. So, remember this was VA and now it becomes VB, plus you have an anti-side defect on B. So, no way, so now you know you see that the structure has lost its order. That is why a simple exchange does not work always. So, therefore, to preserve the order, a sequence of jumps is required. So, now in the second jump, what happens is this vacancy exchanges its position with one of the nearest neighbor atoms of A. So, after that, then the situation looks like this. Now, vacancy is, there is a vacancy at the A sublattice. So, this is VA, plus there is an anti-side defect which was there BA, that means B is occupying the A sublattice, that is the anti-side defect. Now, with this exchange, what had happened, the A is occupying the B sublattice. So, it becomes AB. In the third jump, what happens, the vacancy exchanges its position with this B atom. Okay. So, in that scenario, what will happen, the vacancy will come to this B sublattice. So, that is why you have now VB. Now, both the B atoms are on the A sublattice. So, you have a two anti-side defects on the A sublattice, plus there is one A atom on the B sublattice. So, this is a highly disordered state. Okay. Now, in the next step, what happens is in the fifth, the fourth step, this vacancy now exchange its position with this B atom. So, now it starts to restore the order one by one. So, you see that here in the first three, it resulted in a highly disordered state. Now, it will restore back the order. So, in the fourth step, this vacancy exchanges its position with this B atom. So, now the vacancy has come here if you see, and the B atom has come to its sublattice. So, now you see that instead of 2 Ba, you have only Va plus Ba plus Ab, because one B atom has restored its position. Now, in the next step, the fifth step, this vacancy exchanges its position with this particular A atom, which was the anti-site atom, and therefore, now further what will happen is the vacancy comes to the B sublattice and the A atoms returns to its position. So, you have now only Vb plus Ba, and in the final jump, this vacancy exchange its position with this B atom. So, the B atom will come here. So, you see that now the vacancy has come to this position, and now you have only Va. So, the order is again restored, and if you see, the vacancy started with being here, and now it has come here, and therefore, this net displacement is in 110 direction. So, this type of jump sequence is known as the 6 jump cycle mechanism. So, there are 6 jump sequences that are involved. Similarly, if you have net displacement in 100 direction. So, here you see that for example, this was the situation, you had Va here, and now let us say if it exchanges position with this B atom. So, here it becomes Vb plus Ba. So, Vb means vacancy on the B side, and Ba is the B atom occupying the A sublattice. So, that is the anti-site defect. In the third, so in this second jump, the vacancy exchanges its position with this A atom now, and here it comes. So, it becomes Va plus Ba plus Ab. So, because the vacancy is now moved to A side, so therefore, instead of Vb, you have Va, and there is an anti-site defect on here as well. The A atom is occupying the B sublattice. In the third jump, this vacancy exchanges its position with this B atom, the body diagonal one, and as a result, you have the vacancy moving to the B sublattice. So, you have Vb plus both the B atoms are now on the A sublattice. So, you have 2 Ba anti-site defects, and there is a Ab here. Now, as previously we saw that this is quite a disordered state. Now, it will try to restore the order. So, first the exchange happens with this B atom here. So, that the vacancy now comes here, and one of the B atoms move to its original sublattice. So, you have Va plus Ba plus Ab, and in the fifth step, this vacancy will exchange the position with this A atom here, which was sitting on the B sublattice. So, the situation becomes like this, where you have Vb plus Ba. So, Vb is a vacancy here, and Ba is this anti-site atom, and in the final step, this vacancy will exchange the position with this B atom. So, you will have the vacancy now here, B again goes back to its sublattice. So, you see that again A and B are on their own sublattice, and the vacancy has exchanged the position with this atom. Okay. So, this is what is known as the 6 jump cycle mechanism, and you will see that this is how the exchange takes place. Now, some of you may ask that sir, why the atom chooses to go into such a complicated path? It could have exchanged directly the position here. So, you see that this green atom, ultimately the net displacement is like this. So, why it has to go through all the cycle? So, that is where we say that the diffusion is most likely to happen, or the exchanges that are very readily favorable are the nearest neighbor exchanges. If you see the distance between these two, it is equal to A, whereas the distance between these two, for example, here it is position changing its position with this atom. So, the body diagonal is A root 3. So, A root 3 by 2, which is less than A. So, therefore, this is the nearest neighbor with which it can exchange the position, and that is why this is what is preferred, or this is what with the nearest neighbor. All of these are the nearest neighbor jumps, and that is why the atoms prefer to have this sequence rather than making a long or the second nearest neighbor jump. Okay. There are cases in which I mean, not for B2, but for other structures where this nearest neighbor jump is not at all possible. Then a second nearest jump may be activated. Couple of features: after 6 nearest neighbor jumps, vacancy atom exchange happens such that the order is re-established, and because you can clearly see that A and B both the atoms were involved, so therefore the diffusivities of both the components are not too different. So typically dA by dB lies in the range of 1 by Q to Q, where Q is approximately 2. The upper limit is attained when vacancies are preferentially formed in the B sublattice. The lower limit is attained when vacancies preferentially form on the A sublattice. Then there is another type of defect mechanism. So, triple defect, this is the defect we talked about when we were talking about the structure also. So, you see that here there is a atom which is sitting on the B sublattice. So, this is referred to as AB. So, the B atom which is sitting on its own site is in orange color, and A atom on its own site is in this blue color. So, if you see these three, the two vacancies which are on the A sublattice and this anti-site A atom which on the B sublattice, they form a triple defect. Now, what can happen is that in this mechanism, the first jump happens such that this anti-site atom exchanges its position with this vacancy. So, now you have the vacancy on the B sublattice. And now you see this atom color, why it has changed, because now it has become a, now it doesn't remain an anti-site defect, it comes to its original site. So, now you have these two vacancies here, and now this B atom exchanges its position with this vacancy. So, you have the vacancy here, another vacancy here, and this is how it happens. Then in the third step, this vacancy again exchanges its position with this A atom here. So, the moment A atom comes to this means it is coming to the B sublattice. So, you have a anti-site atom anti-site defect again created. So, now if you see them together, you will see that this triple defect which was present here has now moved to this. So, this is how the atomic motion proceeds in this case, and so this was this is the initial reaction of how the anti-site or the triple defect is generated. So, 2Va plus AB represents the original condition. So, these are found in NiAl on the Al rich side. Remember, NiAl is not a line compound, it has a wider phase field. So, on the Al rich side and the stoichiometric NiAl and also in cobalt gallium, the dA by so this triple defect mechanism is observed, where dA by dB lies in the range of 1 by Q to Q, Q being approximately 13.3. There is one more possibility of triple defect mechanism which involves an additional step. So, for example, the first step remains the exchange with this vacancy. In the second, the B atom exchanges its position with this vacancy. Okay. So, this is the additional step, and then in the third, this B atom again it exchanges its position with this vacancy. So, followed by the exchange of vacancy and the position of vacancy and this A atom. So, again this will lead to the vacancy on the A sublattice and A moving to the site of B, creating an anti-site defect. So, again you see the displacement of this entire triple defect happens. So, this is an additional step through which also such a exchange is possible. Then another type of mechanism that is observed is anti-structural bridge mechanism, ASB for example. In NiAl, this occurs on the nickel rich side, after a percolation threshold is reached. That means this mechanism happens, for this mechanism to be operative, a certain concentration of anti-site defect is required. Otherwise, this will not happen. So, this is usually observed on the nickel rich side. So, this is how it looks like. So, if you have a vacancy on the B sublattice, for example, here, and it exchanges its position with this A atom, and here again this vacancy comes on the A, so it exchanges its position with B, which is an anti-site defect. Sorry, it exchanges its position with A, which was present on the B sublattice. So, this now atom comes here, and the third, so the result of this is that the vacancy moves to the B sublattice here, and this atom returns to this site. So, you can see here this is again in the blue color. So, in this, for example, you see that for such an exchange to happen, the presence of anti-site atom is required, or this involves the exchange with anti-site atoms, and that is why it is known as anti-structural bridge mechanism. Let us look now some of the features of diffusion in NiAl. So, NiAl, as I already mentioned, that triple defect, for the triple defect mechanism, the structural nickel vacancies are dominating defects on the nickel lean side, whereas nickel anti-site atoms dominate on the nickel rich side of the stoichiometric composition. So, if NiAl has a lesser of nickel, then the nickel vacancies are the dominating ones, whereas on the nickel rich side there are anti-site atoms. So, usually the vacancy concentration of at the nickel is much greater than vacancy at aluminum sites, and the diffusivity increases notably on the nickel rich side of the stoichiometric composition. It is practically independent of composition on Al rich side, despite the Ni vacancies being present. And the triple defect dominates, mechanism dominates on the Al rich side, and ASB mechanism on the nickel rich side. This we already saw once the percolation threshold is reached. Then in L12 intermetallics, if you see L12 intermetallics, this is how the unit cells look like. You see that this is the corner atoms, which are the B atoms, and the face centered are the A atoms. So, these are A3B type of structure. Let us now, if you see this structure, each A atom is surrounded by 8 A atoms and 4 B atoms. So, around this A atom there are 8 A atoms and 4 B atoms, whereas the B atom is only surrounded by 4 A atoms. So, therefore, the vacancy motion is restricted only to the majority sublattice, and it promotes the diffusion of A atoms. So, the diffusion of B on its own sublattice requires jump lengths larger than nearest neighbor distances, which are energetically unfavorable. So, the B atom, if it has to exchange the position then into its own sublattice. So, for example, A can do that because there are a lot more A atoms than B atoms, but for B to have the diffusion in its own sublattice require jump lengths which are larger than the nearest neighbor distances. So, the dA is usually given by 2 by 3 A square F C equilibrium vacancy into omega, where omega is the vacancy jump rate, C equilibrium V is the concentration of vacancy in the majority sublattice. Correlation factor has been calculated for such a lattice, and it comes out to be 0.6889. And in Ni3Al, for example, which is one of the prominent examples of L12 intermetallics, the vacancies mainly form on the nickel sublattice, while vacancy formation of in Al sites is energetically unfavorable. And here also the diffusivities of nickel and aluminum are not much different. Minority elements most likely diffuse as anti-site atoms in the majority sublattice. So, with this we end our discussion on diffusion in intermetallics. In the next class we'll talk about the nanocrystalline materials. Thank you.